to be here. I'm perhaps the most foreign one to this group. I'm not sure. I only know a very few of you. It's a pleasure to meet Dr. Silverman. We've corresponded over a few years and have never met before, and indeed we've only now just said hello, but I look forward to chatting. At the very least, I think I can offer you an entertainment. I can show you some nice new capabilities to manipulate matter at the atomic scale, and even now to control single electrons in unprecedented ways using our ability to control at the atom scale. And at perhaps the halfway point in this little talk, I will try to switch gears and show you how some of those techniques, more so the mindset, I think, that I use routinely, can be used to make some very unique sources. So I will try and credit various individuals as I go along. This is the National Institute for Nanotechnology in Alberta, Canada, the city of Edmonton. This is the very quiet characterization area where we have a number of scan probe microscopes and TEMs and laser tweezers and every neat new tool you can think of. It's a very new building, and we've already redug the foundation here and built it again because it wasn't as quiet as we liked. We've already added things over to the side, and it's new but changing quickly. So this is an unusual institute. I'll just say very quickly, it's funded by the provincial and federal government. The whole province of Alberta is only about 3 million people, and the city of Edmonton is about 1 million people. And in good years, which we haven't had this last year or two, we have, for those 3 million people, a budget surplus of about $6 to $10 billion. And so I don't know where that money goes, but a small portion of it goes into this place.
Where does it come from?
People think it comes from the oil sands. So most petroleum in the US actually comes from here, and most people here don't know that. But surprisingly, and most Albertans think that most of our revenues come from these oil sands. But it turns out that things like organized gambling, sponsored by the government, raises as much money. It literally does. So just very quickly, we have very fine facilities, but more important, we have staff, scientists and technicians who run, maintain, and update that equipment. So we don't have stainless steel museums. We have very fine. So there's 200 or 300 people here. There are all kinds of different funding situations. So I want to tell you very briefly about some experiments using scanning tunneling microscopy. You know, this is this remarkable tool that feels essentially a surface at the atomic scale. 20 years ago, Binnig and Rohr and others were able to see these just visible pictures of atoms. A kid like me was able just a few years later to see those atoms much more clearly. This is like the Wright brothers flying for a few seconds, which is far more important than the guy who flew across the continent. Both are needed, but this is the creative step. Now I'm going to tell you about a silicon 100 surface in particular. It's not so important, but what I want to show you is that we can look at a surface like this facet of silicon, the same one which all computer chips are made on. It happens to be hydrogen terminated. That's crucial for what I want to tell you. And we can go in and we can, at will, pluck a single hydrogen atom off a surface. When we do that, we see something like this. So this is hydrogen terminated silicon. These are individual missing H atoms, just to show you the level of crafting that is possible today. This is a little more complicated part of this story. These little white bumps are the same as I just showed you. They're H atoms removed from a surface. This is also that, but it's on a crystal which is somewhat highly doped. And I don't want to get into too many details, but I'd like you to just remember that each one of these silicon atom dangling bonds is a place where one extra electron is localized. And so it's a point of negative charge. And, well, I'll just show you this very quickly. We can make rather amazing things automatically today. So here's a molecule. It happens to be a styrene molecule, which is coming to react with one such silicon dangling bond. This is an unstable species, but can be made stable if it can steal a hydrogen atom. And it always does so in the simulation, leaving a new reactive species. And now you can see this in real space. So this is the first time humans have seen a chain reaction unfolding. We see the initiation site, and then we see the result as a molecule that chemically bonds, reaches over, steals a hydrogen from the next site on the surface, and another molecule follows suit.
What's the time resolution there?
This is over many, many minutes, and each image is just a snapshot of something that happened in a very, very, well, in a relatively small time scale. So it's the pictures take a minute to take, but they are just a snapshot long after what took a nanosecond to occur. So this is a many minutes movie of a few nanosecond snapshots, if you like. We can discuss later.
Yeah, sure, I get it. So this isn't real, then?
This is real. It is a sequence of images portrayed as a movie.
It's like a strobe, right?
It's not a strobe. It's molecules being leaked into a vacuum chamber, cessation of that pressure, looking with the scanning tunneling microscope to see if something happened. On occasion, most often you see nothing has changed. On occasion you see a new molecule has arrived, but it did so long before. Then you leak in some more gas, take another picture, and over time you build up.
Minutes that are searching essentially for something to happen.
Yeah.
But when it happens, it's nanoseconds.
Yeah.
Right.
Yeah.
Okay.
So-
How many frames are there?
There's
in
only
that?
6 or 8 frames here. It's a tiny movie, but it shows you. We can come back to that. Now these are rows of molecules formed by that process I just showed you, and notice that if we image those molecules we can choose to image molecules with a different voltage between the sample and the tip. If we use a sufficiently large voltage, we actually involve the molecules in the tunneling process. We can have a large enough voltage so that we access the molecular states, and the molecule acts as part of the resonant pathway from tip to sample. And so the molecule looks very bright, it's turned on. If we choose to use a somewhat lower voltage, we actually miss or do not resonantly access the molecular states. In that case, the molecules look nearly invisible. What's very odd here is that the molecules, some of them are looking visible at an imaging voltage where they ought to look invisible. So what you actually see here is a 1/r kind of slope near this perturbation. This is a single electron localized at a single silicon atom, and it's causing the molecules to, I'll say prematurely, misusing prematurely, it's causing the molecules to look visible at a voltage where they ought to be invisible. So this is a kind of field effect. You're seeing the molecules are acting as a medium to visualize the electric field. So you're actually seeing the molecules turned on and rather like they would be in a field effect transistor. This is just a Stark effect. So this leads to another silly movie, an entirely fabricated one, of course. And the idea is that if you could have a single atom that you could change the charge of, you could gate the current through a single molecule. And we could talk more about that later, but I'll just skip. So all of that was an aside. What I wanted to show is just that the dangling bond is a point charge if we so choose it to be. And now I'm returning to interactions among charged dangling bonds. So here is a charged dangling bond, dB1. Here's another one. If these were closer, they would look differently. Rather than try and move these in some sense, I'll just pluck off another hydrogen atom and show you that this pre-existing dangling bond looks very different when a neighbor is placed close enough to it. Notice that the other pre-existing dangling bond still has this dark appearance. Now it's a bit of a complex description or explanation, but essentially this is what's happening. We have two atoms interacting. They both have a pair of electrons. If we move them closer, now remember a pair of electrons in this case means 1 minus, not 2 minus. That's simply because of the balancing of the number of electrons and the nuclear charge. If there are 2 electrons, that's 1 extra. So here we have 2 negative entities interacting. If they get closer together, as they are here, if they get closer together, it's a very unfavorable situation. We have Coulombic repulsion between these 2 points. It becomes more likely that an electron will delocalize into the conduction band. This is the band gap. This is the valence band and the conduction band within which these atoms live. So we now have a situation where we have 2 electrons on one atom, 1 electron on another. They're very close together, and electrons can freely tunnel between these 2 points. And so we have something like this. We have 2 atoms freely exchanging an electron, and we have very rare tunneling to the bulk states. And so this is a bit of a summary. I've shown you that distant enough atoms look dark. They have an electron associated with each atom. If we start crowding them together and crowding them more, they get lighter, and this has to do with electron occupation statistics that I'm going to jump over a little bit here because I want to show you something a little different. Now, I'd like to just say to you, even though I haven't fully justified this, that these are 3 atoms on which I know there are 2 extra electrons. You could very reasonably demand more evidence, but if you'll allow me to just say that for now. Now watch what happens when I make a 4th atom here. Do you see that these 2 are darker in appearance than these 2? Let me go back. In retrospect, it's clear that these were slightly darker than this. What we think we're seeing here is 2 electrons simply avoiding one another. They're sitting as far apart as they can. To sit here on these 2 atoms would be an excited state, or here. Now if we offer a new, still 2 electrons in the ensemble, but if we offer a diagonal which is longer than this diagonal, the electrons say, oh, there's a lower energy place to go. And so we think now we are, with our human hands, through the scanning tunneling microscope, not only manipulating atoms, but manipulating electrons. And you see, if we make a symmetric entity with 4 atoms and 2 electrons, you don't see any asymmetry because essentially the 2 diagonals are of equal length and the electrons are freely buzzing around. Now, I'm going to review that and offer one more important observation. I'm going to show you the creation of one of these dangling bond states. So you've seen that before. We could discuss at length why it has this weird halo. This is actually a convolution of the tip, and it's a complexity of the imaging process. Now look at the brightness, just the whiteness of this atom, and watch when we create another dangling bond here. You'll see that this point becomes lighter in appearance, and this is actually the signal that this tunneling event has onset. You're actually seeing first the exclusion of one of the extra electrons, so the thing looks brighter, less negative. And I haven't, but the really important thing comes next, and this I have not shown you. So this is 2 atoms sharing an electron. Now I'm going to put a perturbing atom. I'm going to put another negative charge here, and look what happens. An asymmetry has arisen. So this is kind of like having a homonuclear diatomic molecule perturbed to be like a heteronuclear diatomic molecule. It's ionic-like in a sense. But more important, that asymmetry has been delivered or caused by this controllable perturbation. So I think this changes everything. I think this is a basis for building a whole new electronics. And this could be used to make any number of devices. One thing you'd like to do is make a square entity like I showed you before that had 2 electrons on 4 sites, but I showed you that all 4 atoms look the same. Here we've added a perturbation. We've put these negative charges along this diagonal, and we've actually caused, dark corresponds to negative, we've actually caused the electrons to locate here and avoid here. So again, with a human scale inputs, we've positioned atoms, but we've also positioned electrons. And so it turns out that unlike all kinds of silly, including my own silly single molecule transistor concept that I showed you quickly earlier, there have been many nanoelectronics or molecular electronic gizmos or schemes or just nature papers that are all cute but useless. And that's because people have shown interesting phenomena, interesting structures that no one knows how to deploy. Here we have almost the reverse. We have a mature architecture for a new kind of electronics that Craig Lent at Notre Dame and others have developed over 15 years. And we have come along with the thing that could allow this to be embodied. So what they showed was that if you had 4 quantum dots with precisely 4 quantum dots in an intimate tunnel relationship with precisely 2 electrons somehow titrated into that cell, that, of course, there would be 2 degenerate states. You could arbitrarily label those 0 and 1 binary states. If you could somehow pin one cell into one of those 2 configurations, and then if you could have a family of cells electrostatically coupled, now no tunneling is allowed, no electron exchange is allowed between cells, just electrostatic interaction. You could then transmit information without using electrical current. There'd be a minuscule rearrangement of charge, and you could achieve what some people believe is the theoretical minimum power consumption for transmitting information, storing information, or building a Pentium. And so again, so when this was first demonstrated, millikelvin temperatures were required. Using the things I just showed you, we can do this with atoms at room temperature, not at depressed temperature. So here I'll break, and I'm just about on time. I said I'd go half time on my atom crafting and then switch. So here's an even sillier movie. It's a QuickTime movie, so I think Apple puts in a 15-second time delay if you run QuickTime on PCs just to be annoying. So let's move along a bit. So here's a table with 4 chairs. Here are 2 electrons. And they're repelling one another. So they're adopting the diagonal positions. There may be excited states, but they'll always relax to the diagonals. So this is the intimate tunneling relationship I spoke of. And now here's the next only electrostatic interaction between tables. And you could see that there would be correlated situations, even wave-like situations, but there would be noise, there would be fluctuations. However, you could conceivably pin in such states and deliver information. And with just a little extra work, you could make a computer. And the computer would do all the work that a normal computer does, only it would consume minuscule power, and you see it wouldn't make any smoke. And so now back to our feature presentation. So I could make many summary comments. I think I'll just summarize by saying this, that we can nowadays, or perhaps 10 years ago, we could control matter on the atomic scale And today we can position electrons, and this, I think, opens many new possibilities. And so now, finally, to try and apply some of this, maybe not those particular methods, but as I said, the mindset, I'm going to tell you about sharp tips, such as are used routinely nowadays in field emission microscopes. You can simply etch a tungsten wire electrochemically. It's quite a beautiful process where tungsten is dissolved to make these ionic species in solution. That concentrated dissolved product actually sheathes the tip in solution, causing a necking down and a miraculously fine shape to be created that looks like this. And of course, people have been using this for nearly half a century now. And these tips, if you look at the end, have a 10, 20 nanometer radius of curvature on a good day. And you of course know that if you apply a field to such a tip, you can cause electrons to cold field emit. I'm going to borrow a few pictures from this thesis from a student at McGill. Of course, the radius of curvature causes the field to be enhanced. Well, just quickly, tunneling described by Oppenheimer and Fowler and Nordheim equation, you all know. Mueller in 1936 built something called a field emission microscope, where he essentially imaged that current emitting from a tip with a fluorescent screen. Because the electrons have little lateral kinetic energy, they pretty much just project toward the screen and give you a kind of image of the tip looking like this. And you can actually see essentially variations in work function. And you have something like 1,000,000 times magnification of the tip here. You cannot see atoms, but you can see very fine features, and it's quite a beautiful thing to watch in the laboratory, and it's one of the most simple tools one can build. These things are very dynamic, and you can see adsorbed gases being kicked off, and it's quite beautiful to watch. Mueller noticed, let me accelerate here a little bit. Basically, he noticed that if one reversed the voltage, rather than having an extreme negative voltage on the tip to propel electrons away, if you could put an extreme positive voltage, it turns out about 10 times larger than the negative voltage used for field emission, you could ionize atoms at the tip, suddenly creating a positive species at this tremendously positive potential and rocketing away that positive ion to a screen. And in 1956, he saw atom-resolved field ion microscope pictures. Notice that you have an ion, the species that you want to ionize and then project away from the tip. There's this very beautiful fact that as the atom spatially comes closer to the tip, the point that the object that will take the electron, there's a critical distance. It's good to be closer. It's easier to ionize, to tunnel through a narrower barrier. But there comes a point where you can be too close. This occupied state, if closer, would be energy aligned with occupied tip states, and you could not tunnel in there because you're trying to tunnel into filled states. So it turns out there's a critical distance beyond which you can't get closer and still image. And that leads to the remarkable fact that the ionization process shows an atomic corrugation. So things get ionized at atoms, not between atoms. And, well, this is a rather bizarre picture that if someone wants to, I could tell you later about how trivial data manipulation methods can reveal what at first appears like subatomic structure, but is something quite is actually diffusion information. But this is the thing I really wanted to get to. And this is a thing that was popular a few years ago because it was such a pretty picture, I suppose. But it's more than a pretty picture. So here's a field ion microscope picture of atoms on a tip. Each white bump is an atom. What we've come up with is a way to etch away atoms at the periphery to leave a single atom. Not just a single atom, because other ways of doing that have been created, but a single atom in a very robust structure. Here's a schematic, a kind of PowerPoint movie of how this works. a nitrogen molecule is allowed into the vacuum chamber, and it will act just like the helium imaging gas. It'll get ionized and get shot away. Unless it approaches the surface toward the edge where the field is lower, it can actually chemically react, forming a nitride, and that asperity created can be field evaporated, causing a kind of etching action and eventually a sharpening of the tip. Okay, now these are my instructions to short Excel evap. Just stop. So here is a field ion microscope movie. You actually see the edge of the multi-channel plate. This is about 5 centimeters across. You're seeing individual atoms. You're seeing the field being increased just a little bit beyond the normal imaging voltage to reach the field evaporation regime, where we're ripping tungsten atoms off the tip, and you're seeing atoms everywhere just flying away. But of course, it's like an infinite onion. Every layer removed reveals an identical layer below, and we can turn up the field and see this tremendous effect, and we can turn it back down, and more or less we have the same thing we started with. Now that's very cute to see, but you could have seen that 50 years ago, which doesn't make it any less cute, but that's normal. Now I want to show you something very new. 23 zoom. 23. So this is a single atom tip which we're a little unhappy with, and we manipulate to field evaporate some material. And I'm going to just zoom quickly through this many-hour movie to show you a very interesting effect. Because the tip is getting sharper as we do this etching process, you'll actually see a magnification of the image because the radius of curvature is getting less and the field is getting greater. So watch. See it moving toward you? Maybe I went too fast, but I want to get to the next movie. And then we create this atom size thing again. And then if we had about 5 hours, we could watch the most beautiful thing, and that is that nothing happens. We can just sit there, it just moved. But we've been seeking this and working toward this because this now becomes the perfect source for a new kind of microscope called a field ion microscope. But that's a little different story. So now, one more movie, 271052. These are just measured data. So here, I'm forgetting actually, what do I want to show you? Again, we're tinkering. We're using different field controls. You could just see a flash there of the actual imaging plate. We're with some control, but not with full control. We're manipulating the tip until we get the structure that we want. And
is it still the case though that you're using nitrogen gas to replace tungsten atoms?
yes.
Okay.
And we're tinkering, and we're aware of the underlying structure, even though it is not all visible. That blue circle there was drawn by someone to guide them, and they knew which atoms they wanted to manipulate. And at some point, the desired single atom source was established. And then, again, the beautiful thing that we've been seeking happened. That is, nothing more happens. So
what pressure do you need to do this? Is it hard to, because you say it's so robust, which is seemingly wonderful, right?
These are kind of 10 to the minus 6 torr pressures of helium or nitrogen. And so again, this, you can watch this, and it just sits there.
And then the background pressure before you start?
Is in the 10 to the minus 12 torr range. It's a rather good vacuum. But it need not be. It is in this case because we're interested in making a field ion microscope. I'll say more about that. So what we've achieved in a way is we've taken this thing, which you can think of as a kind of leek, many roots, and we've created a radish. We've created a single point where there used to be many, and this is a kind of electron or ion radish as you like.
Question?
Yeah?
So what's actually happened to all of the nitrogen? Because you showed a picture with N2. Now, unfortunately, there are some chemists here. And of course, N2 isn't a nitride. N2 is a remarkably inert chemical structure.
Right.
And where are they? What's holding them to the surface if they're still there?
It's remarkably inert, except when exposed to a remarkably beastly aggressor, and tungsten will react with anything if it's naked tungsten. So tungsten is ripping apart, and there are decades-old surface science studies that establish that. We do not have a fully detailed knowledge of where every last atom is. We know that we're clearly terminating the surface with some nitride, speaking loosely. We don't know the stoichiometry. We know that it's there. We know that...
Sharp tip that's embedded in a nitride coating.
Yeah, and that's what makes it so remarkably... So for those of you who don't know, nitrides, tungsten nitride is a grinding stone material. It's a tremendously hard material. And so it has been possible in the past to build up pyramids and points of tungsten atoms. But even at room temperature, those will diffuse away. So they're only stable at low temperatures. And this can be raised to almost 1,000 degrees, and it's really remarkable. And it's, but let me, because I'm out of time, let me just